Welcome to the Mining and Metallurgical Society of America webinar series. MMSA is an association of mineral resource professionals whose members represent all facets of mining and metallurgical interests, both domestic and internationally. MMSA has always been a cohesive group of senior people from the mineral industry. The society is dedicated to increasing public awareness and understanding about mining and why mined minerals are essential to modern society and human well-being. The webinar series is one of the ways that we help increase the public awareness. The society concerns itself with fundamental principles and with problems facing the industry in such areas as legislation, economics, and education, as well as environmental concerns, labor relations, and health and safety. Representatives of the society from time to time testify before legislative bodies and provide advice to federal agencies. I'm Betty Gibbs. I'm a past MMSA Executive Director. I will be introducing the webinar today. The title of today's webinar is Can We Make U.S. Battery Supply Chain Sustainable? Lithium-ion Battery Recycling, Current Practices and New Innovations. Azita Yazdani of Exergy Systems Incorporated will present this information, and I think it's going to be very interesting. So let's go ahead and have Curtis Clark, one of our committee members, will introduce Azita.
Thanks, Betty, and welcome to, first of all, Ms. Yazdani to speak with us today, and for all members and guests who are able to attend. Ms. Yazdani is the founder and CEO of Exergy Systems. It's a hardware technology company deploying advanced membrane and electroseparation technologies for the recovery and purification of resources in industrial processing. Ms. Yazdani is a seasoned clean technology executive with more than 30 years of experience in industrial processes and technologies. She is a recipient of Resources Award from the International Sustainability Summit and has served on the Presidential National Advisory Council on Environmental Protection and Technology. She currently serves on the U.S. Department of Energy Critical Materials Institute and its Industry Advisory Council. She has also acted as technical advisor to the U.S. EPA. Ms. Yazdani is a contributor of the Industrial Pollution Prevention Handbook by McGraw-Hill, as well as a published author, and she has presented numerous research and technical papers. She earned a Bachelor of Science degree in Chemical Engineering from the University of California at Berkeley, and is a graduate of the Entrepreneurial Management Program from the UCLA Anderson School of Business. She is also a registered chemical engineer in the state of California. Ms. Yazdani, if you could address us. Thank you.
Thank you, Curtis. Thank you so much for having me. Thank you, Betty and MMSA, for inviting me to give this talk. It's a pleasure to be here. Before we begin, I'd like to give you kind of a little perspective on why I'm into all of this battery ideas and issues. In the most recent years, I've been involved in working with many industrial customers. And in doing so, one of the things we realize is that practically many of our resources, especially the metals, are used and easily wasted in many manufacturing processes. And this has become sort of my mission in life in terms of helping these companies realize these values, recover and recycle resources that could be otherwise maybe used for other manufacturing purposes. And these resources really should not be considered as waste after one use. Which brings us to the topic of today, lithium-ion batteries. We all know the recent trends on, let's see, this thing I should be able to, okay. The ideas about electrification is nowadays becoming bigger and bigger. And we all know that the purposes, the resources that are required to meet this requirement of electrification is primarily metals. So metals like lithium, nickel, cobalt, manganese, and so forth, all of these are going to be key battery materials. They have been key battery materials in the last decade or so. And the demand for the supply of these materials are increasingly requiring that these resources be looked upon and variety of them be exploited, whether it's from mining and brine processing to recovering batteries. As this chart shows, there's going to be a huge gap in supply of lithium just to meet the projected demand that we're expecting in the coming years, about 3 million metric ton of gap. And it's not going to be adequate to meet this with just mining. Anyways, so lithium comes from a variety of sources. It's a very abundant mineral, and we all know that we can get it even from seawater, but the concentration of lithium in seawater is really low, and some of the minerals that we have been processing, especially whether it's rock or brine processing, this has been the main source of retaining or obtaining lithium. But recycling is going to become increasingly a major source of this supply. As I will show later, recycling has its own efficiencies, which will mean basically lower demand on our environmental requirements, on mining timelines, which is one of the major issues in addressing these sources in terms of mining. Today, most of the lithium comes from outside the United States. And one of the things that has become apparent to the US and North American countries is that, we really simply don't have and have not been focusing on developing this supply. Chile, Argentina, and Australia are the main suppliers of lithium, and China also to some extent. But, as a country and as a region, we really lag behind in supplying this resource to be able to sort of secure the supply chain to make the required batteries and required, capacity to produce these kinds of things. Also, lithium mining, of course, it's very resource intensive. It has its own environmental impact. As you can see, this is a picture, I believe, of a mine in Chile that shows the footprint of the processing required for these brines. The environmental impact of these, of course, is enormous, but also the time for processing. I believe typically it takes about 3 years to achieve the concentration that one needs to have in order to get the lithium for better to the next step of processing, which is purification. So this is not going to meet the timelines. As I mentioned, in the next 10 years, we will need so much capacity and supply that we're going to need to look for better ways to get to these materials in order to really meet the demands of the supply chain. And here is just a little depiction of where these materials are needed in after raw materials are produced, they're brought into different cell manufacturing processing, and before that, of course, purification. They're used in cathode manufacturing, and then all of these go into downstream production of packs and batteries that goes into a variety of things, from vehicles to your computer, your cell phone, and of course, aviation eventually, and national defense. So once these batteries are depleted, we have started looking very seriously at recycling, but there are, estimates out there that only up to 5% of these batteries are today recycled. This may not be true so much about electric vehicles, but in terms of everyday lithium-ion batteries that we use in consumer goods and also in variety of devices, the recycling capacity is simply not have been there, and it's believed to be not there today for meeting the requirements. So the US government about 2020-21 decided that this will be a major concern, and we're going to have to look at this this supply chain as we electrify. And so the country has developed a national blueprint. We have developed a national blueprint for lithium-ion batteries, which involves a variety of goals, and I've noted them here. I don't need to go through every one of them one by one, but of course, securing the raw material supply is one of the issues, and there are efforts throughout the country to look at enhancing brine recovery, improving processing from a variety of conventional brine, continental brines, and so forth. Mining industry is sort of really now has focus on trying to look at supplies or exploiting the supplies that are available in North America. But beyond that, I think as we move down the scale, end of life batteries and reusing of these critical materials are becoming more and more of a concern that we have to address. And there has been in recent years companies that have launched, and I will touch upon those briefly, but the capacity requirement that will be expected in recycling has to double in the next roughly 7 years. And so as you can see, the demand will be enormous to have these capacities available across the country to meet the requirements for recycling. Now, why, again, recycling could be better in the long run for all of us? First of all, it takes a lot of brine. As you can see here, these numbers kind of depict the pressures on the environment that we could place in order to reach like 1 ton of lithium. To extract 1 ton of lithium from brine, we have to process about 750 tons of brine. But if you really simply take a lithium ion battery, if you look at lithium ion battery, we only really need to process about 28 tons of that to get about 1 ton of lithium grade material for reuse. And the same is also true for some of the other components like cobalt. And in summary, what this says is that the resources required is a lot less for recycling these materials to mine fresh. Energy consumption is about 82% less, 77% less water usage, and a lot less emissions and costs associated. And as I noted, also probably timelines associated with making and processing these brines. So what is inside of battery? This is just like a real rudimentary overview of what is inside a battery. It's typically anode, cathode, some polymer separated materials. The anode is typically graphite or some sort of a graphite compound that is used. Typically, the cathode is different kind of lithium metal oxides, and these are the different variety of batteries that we make today. Some of them include lithium cobalt oxide, lithium manganese oxide, lithium iron phosphate, and they all have their own little acronyms. And so as you can see in the supply chain, these batteries have typically been designed with different grades of minerals. And these minerals and recovery of these minerals, each one of them could pose challenges as you go into these processing. And we're going to now talk about what are the practices that have been typically adopted in recycling these batteries. Historically, pyrometallurgical processing has been employed, not so much in North America, but in Europe for sure. There's a company, a very dominant company that is continuing and has been doing pyroprocessing. We'll talk about that briefly. Hydrometallurgical processing has been the most recent sort of deployed solution, if I may say, with the more recent companies, both US and Canadian companies that have deployed these solutions in North America and are planning to do so elsewhere. And direct recycling comes with a mixed bag of how it's approached and deployed, and we'll talk about that as well. So when we talk about recycling batteries, a lot of times the very, very first step of recycling batteries is basically collecting batteries and bringing them into a facility which has capability to segregate, maybe dismantle some of the batteries. But the one common thing among many of these sites, not so much with pyrometallurgical, but for sure in the hydrometallurgical and direct recycling sites, they shred the batteries. They shred it so fine that they make a very fine mass, which they call black mass. And this black mass is what is used basically to then process further in various leaching and chemical processing to recover the content. As you see here, we can have anywhere between, concentrations as low as less than 1% to as high as 22% in the case of cobalt. So these are the minerals that are in the typical black mass. And of course, it varies, because if you're taking in a mixed waste, you could have a variety of concentration different days of the week. And you can see the challenges with recovering these materials. It's could be quite complicated, which is one of the reasons why historically the black mass was basically sent off as a feed for a slag into a hydrometallurgical, or maybe even just into smelting facility. It was not necessarily recovered. But now the cost of these minerals have grown so expensively. Lithium, I think as of yesterday, it was $15,000 per metric ton. Cobalt and nickel are also expensive. So, just melting them anymore, putting it in a smelting and mixing it with other ores to sell off in the industry is not going to be, it would not make sense anymore. It's too expensive to just waste this material. And so we'll talk now briefly about the different processing and sort of pros and cons of each. As you can see, this is kind of a picture I found on the web. I think it kind of depicts the idea of pyrometallurgical. We're going to basically be burning in a pyro process these batteries, typically as a pack, sometimes in shredded black mass. And then, sometimes these pyro facilities could involve leaching. I don't specifically, there's very little information about exactly what takes place in some of these facilities. And if in fact they recover any metals, or they just simply create a melted metal mass that will send off to some other processing facility. So this is a very simplistic process, as you can see, but it does generate, emissions. It has intensive energy usage, as you can see. And then also, if you go into a leaching step, it could have wastewater consequences, because those processes are water intensive and chemical intensive and require that water is used and typically wasted. Now, the next common process that
You gonna save this for anything? I'm probably not gonna spend a lot of money. But
the next common process that is used is hydrometallurgical.
Next week.
And hydrometallurgical processing is now become sort of very well promoted in most recent years, and a couple of companies that have made quite a name. Some of them have even gone public to deploy this solution as a way of recovering components of the battery metals. And I found this picture on the web. I thought it was very telling about what a hydrometallurgical activity could involve. In a pyro, you're putting emissions in the air, and you're really wasting a lot of water and some energy as well in there. But in pyro, you have a lot of wastewater, and wastewater and chemical waste is just the nature of the processing in pyro, in hydrometallurgical. And in hydrometallurgical too, I should say that I have heard that the specific segregation is not really well established. So the documentation as to exactly what recovery rates, the performance of these processes, and we'll share some data later about the percentage of recovery rate, is really not well publicized. So none of us really understand well enough whether these practices are efficient enough. Which brings us to sort of our last series of solution, which we call direct battery recycling. Now, direct battery recycling is not really deployed on a large scale today. There are a variety of companies that are doing what we call dismantling and maybe recovering and getting to certain components of the batteries that can be potentially recycled. Sometimes cathode can be re-lithiated. This is the terminology that they use to upcycle the battery. But there's a lot of sort of users of these batteries that have concerns about direct lithium battery recycling, because just segregating these batteries and trying to revive them again, they're worried about, I guess, liabilities, and they're worried about whether this in the long term would be a solution for them, because if they're selling a new car, they want to put a new battery in it. This may be part of the solution, but most of these direct lithium recycling facilities, if any of them are at a commercial scale, they are mostly in trying to dismantle and recover valuable components that can be physically separated with human labor, which in some instances is expensive. And so, which is one of the reasons why a lot of people just put all this stuff in a shredder and make a black mass. Is a much faster process. And if we can get to that material and recover the component of that material, it would be potentially a better quality of recovery of the minerals that we are interested in. I think I picked this slide. I was looking for something that kind of can give you an idea of the efficiencies and what we're really realizing from all of these activities. As you can see, in pyro processing, practically no cathode material and hardly any lithium is recovered. And even in hydro, that seems to be the case. And lithium right now is the most expensive element of the batteries. The other minerals like cobalt, nickel, and manganese are recovered. Copper is recovered. In a lot of these what we call direct recycling, which is again that dismantling activity. Copper foils, some of the plastics, some of the separators, all those things are sometimes recovered, but those efficiencies vary, and not specifically, any one element can be recovered. You can recover maybe a cathode or an anode, but would that be good enough to just use it like that back again? So these are the things that I think industry is grappling with, and I think in the next few years it will all hopefully be resolved in terms of what would be the best strategy to employ to get to the best quality of recovered material that we can get to. So I'm going to talk really briefly about sort of separation technologies. And the reason this is really kind of near and dear to my heart is because I believe we have, in the North America for sure, but in general in the world, we have forgotten about some technologies that have existed, some of them for a number of years, and they have been proven in other industries. And so the opportunity for these technologies, I think, are great to be utilized in these separation and even in some instances for brine processing. So I want to kind of give you a very general overview of what these technologies are or could be. We make some proprietary systems. We have some IP on them, but I think, what I want to attempt to do here is just to give you a perspective of, what electrochemistry can do in separation today. And a lot of the work actually that is being conducted at the national labs as well is directing in that direction, is electroseparation, or, a combination of some of the traditional processing like leaching with electroseparation technologies or membrane separation technologies. So these technologies, as I stated, we've deployed them in a number of industrial settings to recover specific metals, maybe from a specific process. We have deployed them in closing loop factories. So we think that they definitely have a place in this segment, in this industry, in the mining and metallurgical processing and the battery industry. A lot of people conventionally treat these metals and minerals, and sometimes they use technologies like ion exchange, which, it's claimed to be somewhat metal selective, or it can be like cations can be removed with specific ion exchange membranes. But the problem with technologies like ion exchange is that ion exchange, it requires regeneration. Any adsorption, desorption technology requires that once you put those molecules on top of a resin, you have to then take them off, and that typically requires chemicals, and those chemicals are then wasted or, if possible, recovered, but nobody recovers them today. Most of the ion exchange recovery activities ends up in huge numbers of waste, and then also they wash them afterwards. So that tells you there's also wastewater generated, and this is just goes on and on every day, in and out. And in my opinion, it's not a sustainable strategy, especially if you're looking to recover these minerals even in very small quantity, because they're so valuable. What is nice about membranes is that membranes, and I'll show you a picture, hopefully it will give you some idea. There are a variety of membrane technologies that have been introduced into the marketplace, from nanofiltration, ultrafiltration, and reverse osmosis technology, but most of these technologies have not been utilized in what I call industrial separation applications. And the reason has been because the industrial market, first of all, has not really existed in North America in the last 20 years. Most of the industries left the country. And those that are in overseas, they only concern themselves about producing maybe good quality water to come into the plant, but they never cared about, oh, should I recover that water? Or should I recover these chemicals that I'm wasting? The footprint in the industrials have not been a major issue, and only really since recently, since COVID, and since this whole sort of movement towards decarbonization and sustainability has become really big, that we see the demand for these technologies increasing. Customers in industrials are realizing that, oh my gosh, I'm throwing all this stuff away that I'm paying so much money for it. So the same is really true in the mining and metals industry. I think that a lot of these metal values are lost when you mix it with water, when you mix it with chemicals, and you can't really regenerate or recover these when you're in these general processing. Also, sometimes what we do, applying electricity across membrane, and this is called electromembrane separation, can help us really recover specifically ions even. So in a case of electromembrane technology, membranes can be ion selective. So you can have cation exchange membranes or anion exchange membranes. In the case of cation exchange membrane, you can allow cations, the metals, through, and reject the anions that you don't want. And the same, or the other way around with the anion exchange membranes, where you have anion membranes basically allowing anions to pass through and rejecting other things. And so this concept, and believe it or not, there are industrial systems that are built commercially to make, in the chemical industry, for sodium chloride and some other processing. Electroseparation has existed for more than 50 years, but we just have simply forgotten that these technologies can be adapted to applications like brine recovery and mining. Now, this diagram just really simplistically shows the concept. So you have a membrane separation cell, or chamber, if you may call it. It's very much like a battery, and you can apply electricity across that membrane. And what happens is that your solution, what we call maintenance solution, we've actually have built these systems in industrials where we have had, let's say, in a chromic acid bath, we had contamination of nickel, copper, and we needed to remove those so that the bath does not have to be dumped, wasted. So the system receives this contaminated stream, or this solution that needs to be purified, and then by applying electricity across these cell or a series of cells, let's say, you are able to purify, and then we remove the impurities or the contaminants that we don't desire in a collection tank, and it's a very isolated, finite, very small quantity of rejected material. The main solution remains in processing, or it can be put back wherever it was brought from. So, especially like, for example, in some of the geothermal brine, recovery of lithium has been one of the issues. And it's a very challenging concept because you have these huge volumes of brine, which most of it does not have the stuff you want. Most of it does not contain any useful element, but there is some lithium, 200 to 300 parts per million of lithium. So a technology like this can easily sort of answer part of these problems in terms, and these are how a configuration of a small system could look like. I just wanted to show you so you get an idea that these machineries are built today and can be built. And really our interest is to get the industry educated so that they understand there's potentials for these technologies. There's another technology which I think might be also very interesting in brine and minerals processing, but also in the recovery of leachate and any kind of acidic stream. It's a technology that has, again, existed for a number of years. It uses the principles of Donan diffusion. We call it diffusion dialysis. It's, again, a membrane technology, which in this case just uses anion exchange membrane only. And the way we use this technology in industrial processing is as following. We basically, as this diagram shows, we have these acid tanks that has all these contaminants in a processing environment. And we just put these through this membrane stack, and the acid, in fact, passes through the membrane. So if you have sulfuric acid, or even if you have a combination of acids, you can easily pass those through the membrane. And the metals, which are typically the impurities in these industrial processing, these impurities are typically rejected. And so what happens is that you, in fact, you're making a fresh batch of acid every run. And this acid can be brought back into the processing again and again and again. And the metal rejects, we can collect them, we can concentrate them, we can further purify them. So this kind of gives you an idea of how these systems look like. The way we run our diffusion dialysis or acid recovery system, we're able to recover quite a bit of the acid in processing. Typically in industrial settings, customers dump these acids sometimes in tens of thousands of gallons a day. We're able to collect and concentrate the metal reject. So this is, again, a picture of a system that does that. This was on an anodizing facility. It's, again, industrial setting, but these technologies definitely can be utilized. So just kind of in wrapping up, and I can take some questions if you are interested. Battery industry, mining industry is using a lot of dated and sort of antiquated technologies that maybe in the past has worked very well. But I think as we move into the future, there will be interest in finding more efficient processing capacity so that, the footprint for these industries, the energy intensity, the waste intensity is substantially reduced, and hopefully processing time and efficiencies and quality of what is recovered is enhanced. Of course, reducing costs will be the key issue here. And, in industrial settings, we have to show payback. There's not much, of course, not much data right now to say, oh, these technologies are cost effective. But if you don't have a lot of these other elements, the wastewater, there should be enough benefits in terms of recovery of the metals, especially expensive one like lithium, to be able to improve these kinds of processing. And the other challenge also is that, the battery industry is changing every day. People are coming up with new chemistries. People are changing the components of their batteries. And then to just build a process that will only work on one thing or another is not going to work really well. At the end of the day, I mean, I made a notation here that, Panasonic, who makes Tesla's batteries, EV batteries, they basically cut back on cobalt by 60%. So I think that you see the cost pressures are there for these manufacturers to find better, more efficient supplies. As a country, we need to look at what would be the best way to redeploy these industries or really create new industries that will help us become and be competitive. A lot of people have moved, their operations overseas over the years because they thought, oh, they can simply just not do a lot of things overseas. But we see that the whole world is now become one, and we all have to consider the footprint we have. And, all of these ESG demands that are on companies will require them to report on these footprints, no matter where they are in the world. So I think that with innovations and technology capabilities that we have in North America, we should be able to address a lot of these sort of opportunities as they come before us in the future. And with that, I'm happy to wrap it up and answer any questions.
Oh, that's great, Azita. You gave us a lot of information in a very short time.
Thank you.
These slides and the recording will be on the MMSA website. So just go to our webinar list on the website, and you'll be able to look at the recording again, and so you can absorb some of these great things that Azita was talking about. So we do have some questions. The first question is, would you include copper in this story? How much copper is in a lithium-ion battery?
I think I can go back. Yes, I think there is copper there. The copper is typically, it's a copper foil that they kind of cover the anode with. Let me see if one of these slides will have the percentages of copper. So you see, this slide shows that the copper is recovered from the anode. And here in the black mass, there's like about let's say 5% copper in the shredded black mass. So that's the copper. If, there are people who I know recovering and electrowinning even the copper from the anode. And so, that is, copper recovery has been, a big thing in the industries for many years. So hopefully there are people out there doing that. But if it ends up in black mass, it can be recovered as well.
The next question, is there work ongoing on improving battery design and construction to ease or improve the recycling process?
Yes. I know there's a big push, especially, some of the national labs work with some of the battery manufacturers to help them on the design process. By the way, Betty, do you want me to stop sharing the
No,
slide?
that's fine. No,
Okay.
just keep sharing. That's fine.
All right. Yeah, I think that, that will be sort of one of the frontiers that is worthwhile addressing for companies who design batteries and make these batteries. The unfortunate part of it, like I said, has been because most of these have been overseas, and also battery manufacturing is overseas. We talked about how, US is interested to bring that supply chain, maybe Canada as well. But that supply chain today does not really exist. We don't have battery manufacturers, and the sensitivities I believe that we may have in the West may not be the same elsewhere. North America and Europe are more into sustainability and making sure these processes and the redesigning of these batteries will be done in a sustainable manner, so better recycling can take place, dismantling can take place. Yeah, I know it's something ongoing. I'm not specifically aware who is doing what, because this is more on the battery manufacturing side of things, right? So, but I've heard that there are companies are looking into that, and they know they need to do that. Right now, batteries are completely difficult and also in some cases impossible to dismantle. Yeah.
The next question, is there any list of batteries recycling by the state? What are the top states that are recycling batteries around the US?
Okay, so that's an interesting question. So there's a couple of ways one can look at it. There are many states have battery collection and consolidation programs. I know California Cycle, the website CalCycle, for example, you can look up who collects them, who takes them in, where you can drop them off. Some of the stores, I know that Best Buy or some of these companies that deal with electronics, they do take the batteries back. But this is more on the collection side of things. So as I mentioned in the beginning of my talk, there are numbers from 1% to 5%. There's a big debate whether batteries are not being thrown in trash, or especially consumer batteries, right? A lot of the batteries used in your devices, and batteries, maybe even some of people's old phones and so forth. Now, if it ends up in a hand of sort of a dismantler or a recycler, and there are programs in different states, you should check with your state agency. In California, like I said, you can go on the website CalCycle, you can Google, and it will tell you where in your region you can drop off, for example, batteries. Now, that's just one set of issues. There are people who have like services, and they're industrial companies that some are nationwide. one of those companies is called Cerba Solutions. They're probably the largest in North America, as far as I know, in collection of the batteries and producing black mass. They actually have shredding facilities, but they have a huge network that collects these batteries from these different regional and statewide programs and feeds them into their facility where I believe they have one facility in Ohio. I don't know if they have other shredding facilities, but as I stated, these facilities are tough to operate, tough to permit, because you're dealing with materials that you have to first discharge, like the EV batteries. You have to go through a series of steps before you can get to shredding. The smaller batteries a little bit easier. So what happens is a company like that can take these in and shred them and then recover fully or to some extent, right, from black mass. There's not many of those. I think there's a Canadian company that is not publicly listed in the US. It's called Lithium Cycle. They are apparently wanting or have been collecting also battery waste. I think they have or propose to have shredding. They have facility in New York. I don't know to what extent they're operational yet, but they have big plans all over the world. They have raised a lot of money and they want to build these recycling plants everywhere. We also know that one of the ex-founders of Tesla, I don't know if you guys have heard, but he has a company called Redwood Materials, and that company specifically takes Tesla battery packs, and their whole purpose was to get them to be recycled. They both Lithium Cycle and Redwood Materials, they use hydrometallurgical processing, and none of them talk in depth about their performance, how much they recover, what is their success. They both have received a lot of funding. In North America, they both have built plants. I think the Redwood Materials just also got a huge grant, loan guarantee and grants from U.S. Department of Energy to build a plant in Tennessee. So it's a lot of activities going on battery side. Yeah.
All right. The next question. With your list of goals, please consider adding investigation and, where possible, implementation of regulatory permit streamlining with the gap in supply equation.
Yes, I agree. Although, it's funny because U.S. government is now, U.S. Department of Energy in particular, have declared, I think they announced just a streamlined permitting process for battery related processing facilities. I assume that it probably includes battery recycling. So yes, I agree with you. The permitting can always be a problem. In mining is a lot bigger of a problem than citing a facility to recycle the material, the waste material. But in the West, because of regulatory standards that we have, this process, of course, is a major part of getting any factory online, right, that does recycling or builds batteries. But the U.S. has come up with a new initiative that they want to streamline the process. So I hope that some people can take benefit from that.
What percent of recycled lithium can be added to the supply needed as is projected in 2030?
Question. I know that's a big question. I think that if you see from this number, we can add quite a bit. And I think based on this number, there's a need for doubling the capacity of recycling. So that tells you there's going to be huge demands that to be met. I mean, as it is, there's a lot of the battery pack makers, also car manufacturers, are securing the supply because they want to make sure that they have available materials to make their battery packs. Even if they don't make the packs themselves, but some other entity like Panasonic makes it for them. But it's it's a major issue. I don't know. I can't answer that specifically. Sorry.
I'm not sure anybody can, that's unless you can see the future.
Yeah, really.
How, how about lithium ion phosphate batteries or LFP battery? Is technology researched lithium recovery for those batteries?
I don't know specifically. So, most of the work is being done on black mass, and black mass includes all of these batteries. So LFPs is in the category with, lithium, cobalt, or any of these other ones. I don't know what they're doing, if phosphate specifically could cause problems for them in recovery, but I have to tell you, I heard this week that these companies are all having issues separating. So we are to see the success and percentage recovery rate. I don't have any data. There is no data specifically you can find that commercially operating entities have delivered and are delivering recovered materials, and to what quality. And that's also one of the big things, is that the material quality of these recovered items has to meet battery grade. Otherwise, it will not be able to go back into supply chain. So there's a lot of things we don't know. We don't even know if we're even really recovering any lithium today, commercially. There's a lot of science that has been done behind it, but commercially, I can't really say if anyone is doing it.
Okay. American Battery Technology Company is recycling lithium ion batteries of all types at 2500 Peru Drive in McCarran, Nevada, near the Tesla Gigafactory. 1/Panasonic.
Okay, well,
Right.
I mean, that might
Yeah.
be the Redwood Materials facility.
Yeah, you mentioned something about that, and we did have some information about that facility from one of our other discussions. And the last question on the list, how does your technology compare to others in terms of energy use and costs, relative costs?
Yeah, we're not really ready to discuss any of those details. We're not there yet. We're just, grappling with the interest of potentially deploying these, and really in a very small pilot scales initially. So it's too early to tell, but we build closed loop factories every day, and so we believe that we can close the loop on even if we have to do partial hydrometallurgical processing, we can recover and recycle water and chemicals. And that would be the way we would want to build a factory that would recover these metals to the extent feasible, reducing any kind of byproduct costs. To me, a lot of these factories, the expertise is simply not there. And they just go with conventional solutions, and conventional solutions are waste treatment. We think those are costly, right? If we can bring recovery rates and quality of the recovery to be there, which we believe with these technologies we can, it's a lot more accurate of a processing than, let's say, leaching, where you put everything in a chemical and try to get something to precipitate out, right? Yeah, I can't specifically answer that, unfortunately.
All right. That's all the questions we have,
Thank
unless somebody has any at the last minute. Okay, well, I really appreciate you doing this, Azita.
Thank you, Betty.
I think it's been a very interesting presentation, and we will be getting the recording up on our MMSA website within the week. Usually it only takes a few days. And we will have also coming up in the next few months, we still have some more webinars going on. The May webinar will be about mine closure. And we have another one in June on a person talking about aluminum. So just check, we'll be sending out a notice to everybody on this, on our registration list when the recording is up on YouTube. So I appreciate everybody showing up. The webinar is ended. Thank you for coming.